All right, so I'll do the explanations for the exams. Don't worry about these kind of things. I'll also tell you about the time, although these are all announced. All right, so we have seen kinematics, right? In kinematics, of course, we have seen these like what's an acceleration, what's velocity, and things like that, right? That's basically what it is. So we would like to basically establish the relationship between the force and the motion, and that's basically the Newton's laws of motion. So just keep this in mind that, right, accepting this free fall rule, the fact that all objects in the free fall have the same acceleration, this is the first time we see a law of motion, right? This is the first law that we are going to see in here during this course. It's the first one. What do I do in here, right? Okay, so, all right, there's no problem, all right? So that's the first one, right? In this semester, we are going to see other ones like the friction laws, right? The physical laws are basically establishes some kind of a relationship between different concepts, but something that cannot be found by intuition alone, all right? That's basically an example of such kind of a thing. So we can study kinematics by just knowing mathematics. We don't have to look at nature to understand kinematics, right? But to do dynamics, basically, we have to say something about like the forces and how these objects apply some forces to each other and things like that. We actually establish these by stating the laws of nature, right? So the first ones are the laws of motion. Later, we are going to see the Newton's law of gravity. In the second semester, we are going to see the laws of electromagnetism and things like that. So we are going to add more laws, all right, during the whole undergraduate education. So you're going to see many laws, but that's the very first one. And by using these, we are going to actually define our concepts like energy, for example, or momentum and things like that. Some of the concepts that we are going to use a lot later. But these are the starting points, okay? So at this point, we might perhaps explain what a force is, all right? I mean, we have defined what motion is. I mean, this is just kinematics. We use some kind of a reference frame. We measure position and somehow measure time and whatever. We have done some kind of an explanation, but what is force? Normally, in a usual course, I could ask this question to you. I don't know if any of you have some answer to that. But it is something to think about, actually, right? It's one of the interesting questions, actually, because, I mean, when we take physics courses, we actually see these concepts flying around, and at some point, we just accept them, but we never define them in a precise way, okay? So let me try to answer that question. What is force? I think I have also given some answer to that. What is force? The correct answer is that, well, I mean, we cannot define it exactly because I can define things based on something else that we already know. But since this is the first law of nature that we are going to state, we don't know anything before that, right? We only know mathematics, okay? So as a result, if I want to define a concept, I cannot base that definition on anything. So as a result, there is no way that I can define what a force is. So basically, let me just say it like this. The definition of force is, let's say, contained in Newton's laws. So after we stated the laws, we can say something about the nature of the force. And we can also, by using these laws, we can actually measure force, for example, right? So we can define the quantity, we can define a units, for example, for the force. But before seeing these laws, before stating these laws, there's no way that I can define what a force is. I cannot define even its unit, right? We know that, I mean, the unit is somehow is like newtons. It's something that cannot be deduced with things that I already know. So I only know the length and the time, but force actually needs another dimension. Okay, so in any case, so the answer is this, right? I cannot define it. I can only define it after I have given these. But let me just qualitatively see what it is. Let's say it like this. Let's say it like this. Sorry about this. Different objects interact with each other. I mean, they can interact with each other in different ways. Perhaps this is a magnet and produces a magnetic field, so somehow the other one feels the effect of that magnetic field as well. So that's also some kind of an interaction. So different objects can interact with each other. Sometimes they don't, but we're talking about the cases when they interact, which means, let's say, interaction causes something. What does it cause? Causes a change in their physical states. What kind of states can be? Well, I don't know. Their shape can change. They can rotate and things like that. I mean, there are many possible changes. The force is the quantity that kind of captures those interactions which change the emotional state, which changes the kinematic state, right? So in a way, so let's say it like this. Force is the aspect of the interaction which causes a kinematic change. I mean, it changes its velocity, for example, right? That's basically what I mean by kinematic change. So something that changes its shape only probably, or it just rotates, and probably I wouldn't call this as a force. I mean, there might be some other interactions as well that you're going to see later on. But I mean, that's qualitatively how I would describe it. So as a result, in a way, at this point, I'm just making some kind of a connection between the force concept and this kinematic change. In any case, by using that definition, for example, I cannot actually understand that this is a vector quantity. It's a vector property, vector quantity. Right? It's not easy to understand this. Only after seeing the laws of motion, I can understand this. So unfortunately, there's this kind of a difficulty in here. Okay. So in any case, so one of the important things is that, of course, this is basically an interaction between different physical objects, different physical particles, different physical entities, right? Force is basically is some aspect of that interaction that I can quantify. And how I can quantify, I can only see it by seeing the laws of motion, right? Sorry about this ambiguous definition. I cannot do any better than this, but perhaps you can give a better definition. I don't know. In any case, let's just count them by one. Each one actually says a different thing about the force and the relationship between the force and motion. So we start with the Newton's first law, right? So it's called the law of inertia, right, as well, inertia. So, I mean, this is the long form, right? If there is no force acting on an object, and in some versions, we actually replace this with no forces by no net force. So there might be some forces acting on an object, but the net force or the total of all of these forces is 0, then the conclusion is also valid. But let's just say for no force thing, if there's no force acting on an object, then if it is at rest, it will remain at rest. If it is moving, then it will keep moving with the same speed and along the same direction. Okay, so in any case, this is a very verbose definition. By this, I mean that it uses lots of words in here. By using the correct mathematical concepts, we can actually express it like this. So if no if no force, in that case, velocity. Let me actually show this with this sign in here. So we're talking about the vector velocity is constant. So let me write it as an English thing, right? Is constant. Okay. What if nothing changes? A force may not displace an object because of friction, and also object's shape may not change, then it's for definition answered. So it's not a precise definition. So there might be some other kinds of interactions between objects. Some of these interactions may not be properly labeled as force. That's basically what I tried to say in there, right? Okay. As I said, I mean, this is not the best possible way to define what a force is. Okay, so it cannot be certain. I cannot make it certain, and I have explained the reason for that, because I cannot define force in terms of anything that I know, because I don't know anything, right? By using the Newton's laws, but I can relate it to the to kinematics, to kinematic properties of the objects. So then that means that I can use this as a definition of what forces, right? That's something that you should keep in mind here. Okay, so here, the first law basically says that this is the usefulness of some mathematical concepts, and that's the place where the vector concept is useful, right? It's the vector velocity which is constant, because within the statement it says that the direction of the velocity is also the same if there's no force, right? Just keep this in mind. Okay. So in any case, why this is stated as a first law? So some people actually think that, well, this is just a special case of the second law. Why do we state this in this form? There's a reason for that. There's some kind of a historical reason. Aristoteles, right? Sorry about that. Aristoteles. Right, he's the first one. He actually started with this. Let's just remember this. This was the philosophy of nature. Natural philosophy, right? He just said that the somehow, I mean, those philosophers thought that they can understand nature by mind alone. So by just thinking about things, they can understand how the nature behaves, right? But starting with Galileo, and after that, in the scientific approach, we understand nature by doing both of them together. So we first have to do some experiments and then think about them, and then develop theories, and then test these theories by experiments and whatever. Aristoteles in Turkish is Aristo. There's also an old whatever. Yeah, the Greeks actually use these kind of forms as well. I don't know. Philosophy of nature, right? So what Aristoteles has said is that it basically said that no force means the object eventually stops. But Galileo actually has discussed this. Galileo is the first one who objected to that. he said that if there is no force, including that there is no frictional force, he argued that if it is moving, it never stops and it keeps moving. And this is the correct way that of thinking about it. So Galileo was able to understand it, but nowadays we can actually see this really. So for example, in space, since there is no air friction, for example, we actually see that this is the case. So if you just throw something away, it just goes on forever. In any case, so it's basically a correction to this. So Galileo was the first one to notice this. After that, Newton realized the importance of this. As a result, he actually adopted it as the first law, right? Nowadays, we also use this for defining another important concept. So this is what we call as an inertial reference frame, okay? So that's a definition, all right? So that's a definition of an inertial reference frame. We define a reference frame as inertial if the first law is valid within that frame. So that means if you just observe within that frame an object with no force acting on it, an object where there is no force on it, if that object moves with constant velocity, then you would say that this is an inertial reference frame. Okay, so that's the definition.
Hocam,
yes.
Would you give an example that is not inertial reference frame?
The Earth is an example. Yeah, there are many examples. I mean, if a bus is accelerating, for example, I don't know, it's something like that. It is accelerating, right? It's speeding up. In which case, if there's some kind of a ball on the floor, so you're going to see this ball to be rolling to the backside, right? Even though there is no horizontal force acting on it, it appears like accelerating relative to you. So as a result, bus is not an inertial reference frame.
But if we are outside the bus,
if you are outside, if you are using an outside reference frame, so that would be inertial.
Oh, okay. Okay, now I get it. Okay.
I mean, it doesn't matter whether you are inside the bus or outside. So are you using the reference frame of the bus, basically a point inside the bus as an origin, and it moves with the bus, for example. This is bus's reference frame. An outside reference frame is basically a point which is fixed on the ground, for example. That's basically how I use these kind of things. We would basically assume that this is almost an inertial reference frame, almost, but apparently in here, bus is obviously not an inertial reference frame, right? Because, I mean, some object in here, for example, that person which is at rest on the ground, for example, even though there is no horizontal force acting on it, or there's no net force acting on it, relative to the bus, the person appears to be accelerating. So therefore, it's not an inertial. Bus is not an inertial reference frame. So that's almost an inertial reference frame. Why do we say it's almost? I'll explain these later, but in any case, we know that the Earth is rotating around itself. It's also rotating around the sun. So this is actually an accelerated motion. So the ground in here is in an accelerated motion. It's just like a bus, so therefore it's not an inertial reference frame. But in any case, I mean, what's important is the definition in here, right? So basically, we would like to express the physical laws in reference frames where they are valid, okay? Because, I mean, since the first law is a law of nature, it should be valid in a valid reference frame. So as a result, that's why we are talking about these kind of reference frames. So obviously, what I'm saying is this. There are some certain other kinds of reference frames in which the laws of nature are not valid, okay? So we don't want to use those reference frames, but we would like to use the reference frames where these laws are valid, And for this reason, we just define this concept of inertial reference frame. All right. So let me pass to the second point, right? So I'm just going to use this thing. So suppose I have a reference frame that with origin A, and let's say that I have another reference frame in here. Let's say C, for example. I mean, this might be a car, for example, which might be moving with some constant velocity, right? So the statement is this: if by a reference frame in here, let's just remember what reference frame is. This is origin plus axes, okay? Just keep this in mind. We define the reference frame as a chosen origin and chosen axes. If I choose the axes in a different way, then that's a different reference frame, right, in principle. But here, to simplify things, I'm going to assume that the axes are the same in all of these different cases. So in here, only the origins of the reference frames are different. And these origins might be moving relative to each other, all right? Just keep this in mind. In this course, actually, I won't be talking about, just forget about it, sorry. Let me just write this thing down. So if A is an inertial reference frame, A is an inertial reference frame, and if B moves with constant velocity relative to A. Why did I say B? I should say C. B moves with constant velocity relative to A. Then C is also an inertial reference frame. Okay, so that's our important statement. The proof is very simple. So suppose that I would like to look at the motion of an object in here. So I just call the object as, I don't know, let's say P, for example. So we know that the acceleration of P relative to A, for example, or relative to C, that's equal to the acceleration of P relative to, yeah, let's just remember this formula first. So that's the relative acceleration, right? So therefore, the acceleration of P relative to the frame C is AP minus AC. Now, if I measure them relative to A, so we have this thing in here. So we know that since the velocity of the C relative to A is constant, that's the same thing as saying that the acceleration of C relative to A is 0, which means that this is 0. So that means acceleration of P relative to A is the same thing as the acceleration of P. I mean, in both frames, objects have the same acceleration. So let me write this thing down like that. So objects have same acceleration in both reference frames. Okay, acceleration is not a relative quantity in this case, right? It has the same value in all frames. So therefore, if you just look at the definition, so if P is an object where there is no force on it, therefore its acceleration is 0 in this inertial reference frame. In this frame, in A frame, the acceleration is 0. And because of this property, the acceleration on the C frame would also be 0. So therefore, C is an inertial reference frame. Okay, so this statement basically follows from the definition, right? That statement. Okay. Basically, if your reference frame is moving with your constant velocity relative to an inertial reference frame, then your frame is also inertial. Okay, so That's essentially the relativity principle. But it is expressed in a different way. Let me just say it like this. I can also express it like that. So A is an inertial reference frame. Let's say this is given. In that case, I can say the second statement. So C is inertial if and only if C moves with constant velocity relative to A. Constant. Okay. Let's say it like this. So I can decide if a reference frame is inertial or not by just looking at whether it is moving with constant velocity relative to A or not, right? Relative acceleration is 0, yes. So that's the first statement. Let's talk about another reference frame. Let's say B is the accelerated bus frame, for example. B is not inertial if and only if B accelerates relative to A. Okay, so we just call these as, so it's the same thing, right? Same logical statement. A reference frame is inertial if its relative acceleration is 0. It is not inertial if its relative acceleration is not 0. If I know that some reference frame is already inertial, then I just need to look at the relative acceleration with respect to that frame. All right, so these kind of things, frames are called accelerated reference frames. Or some people just call these as non-inertial. Okay. So what's important in here? So that's the thing that I'm going to state in here. So the inertial reference frames, these ones in here, are reference frames where all laws of physics are valid. Right? But these accelerated reference frames, so let me use a red color in here. I didn't choose the red color, all right. So accelerated reference frames are frames where some laws of physics are not valid. Okay. Example, the first law of Newton's first law of motion is not valid in accelerated reference frames, right? By definition, we know that. We also know that the second law of Newton's second law of motion is not valid. There are some laws which are valid, like the third law is valid, whether the reference frame is accelerated or not. So that's independent of the reference frame. There are some laws of electromagnetism that we will see later. They are not valid in accelerated reference frames, right? So as a result, these are the reference frames that we don't want to use, right? Don't use them. Right? Unless you know what you are doing. Right? That's important actually, but that's something that I'm going to stress on later. Yeah. So use only inertial reference frames because all the laws of physics that you are going to see in this course or later, whatever, all laws of physics will be valid in inertial reference frames. Some of them will not be valid in the other ones, right? And that's the reason why we don't use these other reference frames. Okay, so that's important. So again, let's remember, so that's the definition basically. By using the first law, we define, or we kind of test whether a reference frame is inertial or not. So we just define these inertial reference frames. But from now on, whenever, if I don't say otherwise, we are going to assume that we always use inertial reference frames. Will we study non-inertial reference frames in general relativity? The problem with general relativity is that in these kind of situations, there are no inertial reference frames. Actually, you cannot find any because of the curvature of space and time and things like that. And so as a result, you have to use the other reference frames, right? It's actually quite complicated in general relativity, right? So as a result, there's some kind of a relevance of that discussion to that topic, but it's too complicated actually. Okay, let's go to the Newton second. Yes.
Teacher, can I ask you a question?
Yes.
If A and C has the same acceleration, what will we do?
What do you mean? We should talk about the relative acceleration.
Yeah. A and C have the same acceleration compared to each other.
Yeah.
So can we apply?
I mean, when you say acceleration, you're saying you just measure the acceleration relative to some kind of a reference frame. So you're saying that these two frames have acceleration relative to a third frame.
Mm-hmm.
That's okay. What you're. So in that case, they are not accelerating relative to each other.
Yeah.
All right. In which case, if one of them is an inertial frame, then the other one is too.
Okay.
Right?
Mm-hmm. Okay. Thank you.
All right. Yeah. Somebody has said, well, the relative acceleration is 0 if both of them are in free fall, for example. That is a nice example. Both are accelerated reference frames, but the relative acceleration is 0. But since they are not inertial, none of them is inertial reference frame. Both of them are accelerated reference frames. All right, whatever. Right, let's just quickly go over this Newton's second law. So it basically relates the net force on the acceleration. So that's the one that we use a lot. So implicit in here is the statement that force is a vector concept. And so as a result, if there are many forces acting on an object, to compute the net force, I have to take their vector sum. So I can compute the vector sum in this geometric way, or I can use this algebraic formulation. Sorry about that. So F net will be basically the sum of these forces. I can also do the same thing component-wise as well. So I just look at the x component of the net force. So that's going to be the sum of the x components and so on, right? Yeah, let me say etc. in here. I don't want to write everything down. But in any case, so the net force is therefore the vector sum of all of these individual forces. And the Newton's second law says that the acceleration is basically in the same direction as the net force, but there's a proportionality between the acceleration and the net force, and the proportionality constant is called the mass. All right. So next question is therefore, what is mass? I mean, just like the question, like what is force? I can also ask the what is mass question. I don't want an answer from you. I don't expect, but something that you can also ask yourself. In high school, I know that you learn the mass as, you define the mass as amount of matter, but it is incorrect. That's not the correct definition, and sometimes people get confused by these kind of definitions actually. So again, just like force, the mass concept is the concept that meet for the first time, and it just appears in here. So as a result, by just looking at this equation, I have to define what mass is, right? So here we will just say that the mass is a measure of inertia. Okay. Don't worry about this thing. I'm going to discuss this issue later. when we also see the gravity in the gravity chapter, because mass also appears in there as well. So as a result, it has a second definition. So here, it just plays the role of basically expressing the amount of the inertia of an object. So think of it like this. So there's a truck in here, for example. This is a truck. And think of it, I don't know, some kind of what do they call these baby things? I think they call it as a stroller. My English is actually quite bad with these kind of things. So suppose that you apply the same force on both of these objects. So you apply a force F to the truck and the stroller at the same time, let's say. Which one has a bigger acceleration? So we know that the stroller has a bigger acceleration. So therefore, the kinematic state, the velocity of the stroller changes easily. So that means this one has a smaller inertia, let's say less inertia. The truck has more inertia, right? But by measuring the amount of the inertia that they show to applied forces, by quantifying with the mass in here, I can basically state this fact by stating that the mass of the truck is bigger than mass of the stroller, right? This is basically saying the same thing, that the truck has more inertia than the stroller. Okay, let me just state it like that, all right? I don't want to say anything further about this. How do we measure mass? Well, this is one way of measuring, right? You just apply a force on the object and measure its resultant acceleration. By just looking at the ratio between them, you can measure the mass. Okay, you can also weigh them. That's another way. That's the common way that we use to measure masses. But there might be some situations where we cannot weigh objects to measure their masses. Like, for example, when you are in space, for example, how do you measure the mass of an object? The answer is this, right? I mean, you just use this law in here. Somehow you have to have some way of measuring the forces. You can measure acceleration because it's a well-defined quantity by using some kind of, I don't know, the distance measurements and times and things like that. By doing that, you can measure masses, okay? Yeah, in any case, I can also postpone this discussion to a later point. All right, the third law. Right, let me quickly do this because this is the compulsory part that I don't want to spend too much time on this. So this is also called the action-reaction principle or the action-reaction law. But in any case, the idea in here is this. We say that two objects interact with each other. And during that interaction, each object applies a force on the other one. And so as a result, if that force is non-zero, then the force on the first object should also be non-zero as well. So as a result, forces are applied to both of these, each of these objects, right? So there are at least two forces for each interaction, therefore. The third law says that the magnitude of these two forces are the same, but the direction is opposite. So we are not going to question this or try to justify it, but we are just going to accept it as it is. So that's one of the fundamental laws. Later, we are going to see its relationship with this, with these other concepts that we are going to describe. So that's one of the important laws of physics. So when we are solving problems, we are going to use this in some places, but here yeah, let me just describe it. So in formula, in a mathematical way, I'm going to describe it like this. So this is the notation that I'm going to use sometimes when two objects A and B are interacting. A force is applied on one of these objects, let's say A. If a force is applied on A, it is applied by one other object. So as a result, for each force, there's these two properties. Who is applying the force, and it is applying on whom, right? There are these two aspects in here. So as a result, let's say that force applied by B on A, I'm going to show this by FAB. The other force applied on B by A, I'm going to show this FBA notation, okay? So let me undo and do these. So basically, the third law says that these two forces are basically related by that vector relationship. They have the same magnitude, but opposite direction. Some people have some confusions about these. Let me just talk about this, right? Is there a time delay between these forces that we mention in action-reaction form? Can there be a force on an object, but it is not applied by anything? Is it possible that there can be a force on an object, but it's not applied by anything? So I could have actually asked these in some kind of a quiz question. Right, there are some misconceptions, so that kind of clarifies these. So let me just give a break in here, right? Let's say that, let me just write my note in here that we will meet. So font size is too big. So let's meet at 1340. I mean, just think about these two statements. So I'm just going to give the answer at the beginning of the second hour.